Today we're going to be hearing from Ilenna. Her talk will be about 20-25 minutes, and then there'll be time for questions and discussion afterwards. Please keep yourself muted during the talks, but feel free to ask questions in the chat. I have to let you know that we're recording the videos. That's because they will eventually be on YouTube afterwards, so you can go and enjoy the talk again. And yeah, just to introduce Ilenna. Ilenna majored in neuroscience at Dartmouth College and then worked as a research technician at Johns Hopkins. After that, she started a PhD in neuroscience at UPenn with Conrad Cording, and her work focuses on dendritic computation, and that's what she's going to tell us about today. So yeah, with that, I will pass over. Thanks.
Thank you, Marcus. My name is Ilenna Jones. I'm in the recording lab at the University of Pennsylvania. So the question that my work tries to answer is what's here in bold, which is can a single neuron solve MNIST? And I'll define that kind of point by point. Well, not quite point by point, but I'll be defining that in the later slides. But the takeaway is in the subtext, which is that neural computation of machine learning tasks emerges from the interaction of dendritic properties. So, but first, before we get into that, what is the big picture, or my big picture goal? And that is to ask the question, how do we understand the brain while constrained by our understanding of its smallest computing units? What are those units? Well, controversy aside, let's think of neurons as the smallest computing units. So, however, when we think of that, we're kind of taking a big bite out of the brain. The brain's made up of neurons as well as other cells, and neurons are quite complicated, as you can see just in their morphology. But there are also many aspects of single neurons beyond morphology as well that people have been able to find through various experimental investigations, such as conductance distribution, or where exactly and how many are there of voltage-gated ion channels along the dendritic tree of a single neuron. And even in the dendritic tree, not only can you find spiking in the soma, but in the dendritic tree, you can get spiking there, how those spikes then travel down the dendritic tree or up the dendritic tree to be integrated for an action potential decision. Even when it comes to the inputs into the dendritic tree, the location of those inputs, which are at synapses, is a big question. There can be clustering of correlating presynaptic inputs as well, leading to very nonlinear events. And there's actually been investigation showing that there are certain forms of computations happening in the dendritic tree, such as coincidence detection. For example, it kind of reflecting the AND gate or AND logic function, and as well as the XOR logic function using specific ion channels that people found in 2020, looking at human neurons and modeling them. Lastly, there's even inhibitory control. There's inhibition happening in the dendritic tree, changing the gain of the excitatory activity in the dendritic tree. And lastly, a lot of these things are plastic. They change over time and experience. So, and there's also many other things that are in this diagram, but we want to know how these smallest computing units are computing and try to figure out how that ability to compute might be usable for constraining our understanding of the brain. So how might we determine in what way any of these aspects contribute to a single neuron's ability to compute? There's so many properties. What are they doing? We can begin to answer this using models of single neurons. But we brought up so many different aspects of them. How do you define a single neuron model? What do you include? So we can define a single neuron on a spectrum of abstraction. So on the far end of abstraction, we can actually find the McCulloch and Pitts neuron, which is one of the first, if not the first, neuron models put forward, kind of laying the foundation for computational neuroscience. And these neurons are very simple. They're literally just a linear weighted sum of inputs put through some output nonlinearity. And that's on the far end of model abstraction. On the far end of biological realism, you have not only the morphology at play, but all of these different aspects of neurons included in your model to try to best to make the most biologically realistic model of a neuron as you possibly can and simulate it to be able to learn some things about neurons. But that can be computationally resource heavy. And on the other side, having all of these empirical details that we are modeling in our neuron model allows us to answer certain kinds of questions. So people strike a balance, such as with the cable model, where you might have passive electrical properties, and included might be voltage-gated ion channels, but that might be it, right? Some empirical details are included, but not others. And this has been very useful to answer certain kinds of biological questions. And it's almost precise. So what I want to do here, though, is I want to kind of take a step into, well, some of my background and training is in deep learning. Some of the work that I decided to do is inspired by previous work where they've taken a deep learning architecture actually and changed it a little bit to make it more neuron-like. It's a very abstracted neuron model, but it has empirical properties, or in these other papers, it has empirical properties putting it on this spectrum. Of course, now I want to backtrack a little bit. What is an artificial neural network, which I posted here? So what is an ANN? And just briefly, an artificial neural network is a network of neuron units, like so here, that are linear weighted sums mapped through a nonlinearity. So this is a linear weighted sum put through a nonlinearity, which is like the McCulloch and Pitts neuron, actually. So turns out that model of a neuron has been leveraged to great effect to produce deep neural networks that we know, especially now, are very powerful in being able to learn or compute tasks, which is very powerful. And so why don't we try to take advantage of that? Can we have a neuron model that we can train to be able to compute a task? And one way to best reframe this is, can an artificial neural network with biological or dendritic properties be defined as a single neuron model? What might we learn from doing this, right? So we can ask the question, can a neuron like ANN even do complex machine learning tasks? And if we introduce dendritic properties iteratively, how does each impact artificial neural network performance on a task? What are the individual impacts of dendritic properties on an artificial neural network's performance, while simultaneously making the artificial neural network more neuron-like? So this leads us to a hypothesis. Adding biological properties to move toward biological realism will impact artificial neural network performance. We don't say, we're agnostic to it will improve. We're agnostic to if saying that it will decrease or impair performance. We're just saying it's going to have an impact. Let's explore. So how do we do this? Well, we have to choose what dendritic constraints we are adding to or imposing on an artificial neural network to make it more neuron-like. So in two papers, I talk, the first of which I talk about these two constraints, which is, I think the first constraint is probably one of the most important constraints to make this analogy to making an artificial neural network more neuron-like. But we take the morphology of a dendritic tree and impose it onto an artificial neural network. This is an artificial neural network here, where if you look at just the left side here, you have inputs coming in at the top layer, going through a dendritic, what we would then argue would be similar to dendritic compartments or these units, and then coming together to an output node, which will either produce a value between 0 or 1, usually either 0 or 1. So it's a binary input and binary output. So a binary branching structure adds a lot of sparsity to this network, and it's very strict. Second constraint is synaptic repetition. Based off of previous studies, experimental studies, on average, about a presynaptic neuron can synapse onto a postsynaptic neuron receives a presynaptic input on average 4 times from the same single other neuron. And so we decided to add synaptic repetition to our model in this way. So without going into too much depth of the 3 other constraints, I'll just say that at each unit, there is an output nonlinearity. Remember, these are all McCulloch and Pitts-like neurons. So there's an output nonlinearity. I replace it with a dendritic nonlinearity. I add synaptic nonlinearity to the top layer, and I encourage non-negative weights between the dendritic units in order to move closer to this analogy of a compartment-like model where only the adjacent compartments are connected through some sort of conductance weight or an axo-resistance weight. So, oh, and conductance and resistance, they're positive numbers, so they're non-negative. That's a lot of detail, but what I want you to come across, I'm going to go into more detail about this moving forward, but so don't worry about remembering all of these right now. But what I want you to really take away from this is that as I add each constraint, I am moving closer, maybe not in these huge steps, but closer toward biological realism with each added constraint. So thinking about the binary branching structure that I did go over a little bit. So the binary branching structure of dendritic trees can be imposed onto an artificial neural network like so. And say you have these repeated inputs. So 1, 2, 3, and 4 are unique inputs. We assume that these inputs can be repeated in the same way in other subtrees of a dendritic tree. So we built an artificial neural network with repeated inputs, which also corresponds to repeated repeated subtrees or adding to the morphology. Of course, it's like, okay, this is a bit strict, a little unrealistic, but we wanted to see how the synaptic repetition had any kind of effect. So we added it. And you can see with the second constraint, it adds a lot more of these black lines, which are weights or parameters to the model. And a big rule of thumb in deep learning is the more parameters, the easier for the network to learn and perform. So we need a control. So what we did was we took a very simple artificial neural network, a fully connected neural network, as opposed to this very sparse and deep network. We have this one-layer neural network where we scale the number of nodes in the hidden layer to be 2 times the number of subtrees in the K-tree model. Or I call it a K-tree model. Let me see. K is equal to the number of subtrees. So, and when you do the math here, they come out almost equivalent, and they scale they scale in the same way. So last but not least, there's a, maybe last but least, is the lower bound control that we wanted to add, which was this linear point neuron model, which is really just a single unit receiving a linear weighted sum of its inputs. And it would correspond to a single compartment model of a neuron called dendrites. So this linear point neuron model is our lower bound. Our fully connected neural network control is our upper bound, and we have our K-tree model. So let's see what the results. Oh, but first, they're performing on what? They're performing on a task, and this is where I get to MNIST. So MNIST is a image data set of handwritten digits. So we made this a binary classification task where we only show the classes 3 and 5, and the neuron is supposed to produce a output of 1 when it sees a 3 and an output of 0 when it sees a 5. And we can calculate an accuracy measure based off of how the neuron model responds to each input. So here's our results, where the x-axis is the architecture size, K, where K corresponds to each repetition or each subunit, each subtree. And we basically double it as we go from left to right to an extreme level with 32 repetitions. So in the y-axis is our accuracy on the MNIST task. So what I want you to focus on is the K equals 1 condition, where only the binary branching structure constraint is at play. And you can see here that the fully connected network, our upper bound, is much higher than our K-tree performance. And if you look at the linear point neuron model performance, it's actually much lower. So this is kind of what we expected, where this is our lower bound, this is our upper bound, we're in between. However, when you increase the number of repetitions or subtrees, same thing, you can actually see that the performance of the K-tree and the upper bound are indistinguishable at extreme. So in essence, binary structure reduces performance. If this is our vanilla ANN, this is a reduced performance. And synaptic repetition improves performance. So the takeaway from this is that structural constraints can affect performance, but it's not necessarily the case that every constraint you add improves performance. Sometimes it reduces, sometimes it improves. So moving back to the constraints that we're adding, let's just keep adding more. So, and see what happens. So the dendritic nonlinearity I'll talk about now. So we thought that the, let me just go back. The ReLU or leaky ReLU activation function at each of these white nodes or dendritic nodes is something that we can pick on here and replace. So the dendritic nonlinearity, or the NACAK function, is really just a linear weighted sum of sodium, calcium, and potassium current voltage curves, adding a linear function as well, which makes a line with a bump in it. And, but this bump is a very interesting bump, but we'll talk about that later. It's formalized here, and it's really just the linear component, which is the adjacent upstream compartments being received by the unit in question, sodium, calcium, and potassium components. And what we're going to do here is that we're going to take this dendritic nonlinearity and compare it to the performance of the artificial neural network with these other nonlinearities, being ReLU in red, leaky ReLU in pink, sigmoid in purple, and swish in green. Swish is this almost like continuous version of a indifferentiable version of a ReLU function. So what if we replace ReLU with a dendrite nonlinearity? We've got our 5 different conditions, but what I want you to focus on is what is in gray, which is the dendritic NACAK function, and just look for it in the binary tree model that we are using with synaptic repetitions. So it's the same kind of graph as before, only the different conditions are activate different activation function or output nonlinearities. And you can see that in gray, you actually have much better performance than with ReLU and leaky ReLU and even sigmoid. But up there still is the swish function, which is very interesting. And then just to remind you what this looks like, each of these nonlinearities are very different. And what you can take away from this is that the dendrite nonlinearity performs well with the binary tree model as opposed to the ReLU or leaky ReLU models. So what if we do the same thing with our fully connected control? So we have our fully connected neural network model, and we're doing the same exact experiment, just with a different architecture, with a different kind of morphology, quote unquote. So in gray, you have the dendritic nonlinearity actually performing much worse than the ReLU and leaky ReLU models. But if you look closely, in gray, we're around 95% accuracy, and that's just a little less, but just about the same as in the binary tree model. So what's we're really seeing is that the ReLU and leaky ReLU models are actually just really good with the fully connected network model. And this might be because the ReLU and leaky ReLU activation functions add sparsity to our densely connected neural network model. And some of the benefits of sparsity can be found in the seminal paper putting forward the ReLU as an activation function in Gloro 2011. I'm not going to get into it here, but it just so happens that the ReLU nonlinearity sparsity seems to impact model performance, where a binary tree model with ReLU performs worse, probably because ReLU adds sparsity to an already sparse network. And in a fully connected neural network model, it performs much better. So lastly, the last 2 constraints, the synaptic nonlinearity and the non-negative conductance weights. So I'll talk about the synaptic nonlinearity next. So we have to build it. So the synaptic nonlinearity is added onto our K-tree model or artificial neural network as the first layer or of input, where the input is received, and then the output of the synaptic nonlinearity is received by the rest of the dendritic tree-like structure of the artificial neural network. And how we built this was we had an equation for current flow and it has capacitive, excitatory, inhibitory, and leak components. This is not a real synaptic equation because it has both the capacity to be excitatory or inhibitory, depending on how this is parameterized. But we allow for the synapses to be excitatory or inhibitory based off of how they're parameterized. That's the benefit of this kind of formulation. And then the conductance term here for excitatory and inhibitory terms are defined by a positive exponential function where x corresponds to the input received by the model unit, where x would be a value between 0 and 1 because it comes from a normalized, it comes from a pixel input from MNIST. So and each pixel is between 0 and 1, and it is parameterized with alpha 1 and alpha 2. Doing a little algebra, this is the nonlinearity with steady state voltage. And the takeaway here is that there are 5 learnable parameters per synapse. These alpha terms for excitation and inhibition, and a leak conductance term. And a takeaway from this also that is not depicted here is that the distribution of activities that might be output from the synaptic nonlinearity is between the value is in millivolts, and it is between the values of negative 70 millivolts and 50 millivolts, which is very important. So adding synaptic nonlinearities and non-negative conductances gives us the following results. There are 6 different conditions, but I want you to focus on just 2, where you have both the synapse nonlinearity and the non-negative conductance weights given to a K-tree model with all of the previous constraints as before, and a fully connected network control that is exactly the same in all of the constraints that is added. And one's in orange, one's in red, look for those in the results. So again, we have the x-axis where K is increasing for synaptic repetitions. You have accuracy here, and this is the performance of these models. So in red, which is the fully connected network performance with all of the constraints, performs okay. And then with orange, which is the K-tree neural network with all of the constraints, it actually performs best out of all of our different conditions. Why? So synaptic nonlinearity scales input to match dendritic nonlinearity. So what I mentioned about the synaptic nonlinearity is that if you don't have a synapse, the input to each unit is between 0 and 1. But if you do have the synapse, the input to each dendritic unit is scaled to negative 70 and 50. This matches actually our dendritic nonlinearity range. So in this scale of negative 50 to 50, you have this squiggle with a bump in it. The bump is pretty big. It's changing between negative 50 and 50. But if you remove this line here, you have only the ion channel components. And it seems very interesting between negative 50 and 50, which is exactly how the input is scaled to be received by the network with these dendritic nonlinearities. So there seems to be a matching of these different properties. So the takeaway here is that the model with all biological constraints results in the best performance, likely because of a synergy of some of the properties that we added. So there's some limitations with this work. We use very highly symmetric dendritic trees, which are not representative of most real neurons. So further work must be done, and has actually been done in OJA 2022 on asymmetrical dendritic trees. And our model is a feed-forward artificial neural network. Neurons are not feed-forward. There are no temporal dynamics in our model, which are necessary for reproducing dendritic phenomena. So further work of this kind must be done in temporally dynamic dendrite models. In conclusion, our hypothesis was that biological constraints added to an artificial neural network affects performance of that neural network on a task. And that came out to be true. And in fact, it's not necessarily the case that every constraint improves performance. Some constraints decrease performance. But overall, when you add all of these constraints together, these constraints can perform better than a controlled, densely connected network. And lastly, these biological constraints can synergize together, leading to higher performance in their ability to learn and compute a complex machine learning task. And that's it. Thank you so much.
Cool. Well, thanks so much for the great talk. It was, yeah, I feel like I learned a lot and have lots of questions. But yeah, first there's a question from the chat. So Michelle Nardin says, wonderful work. Question, did you train your ANNs? There's sort of two questions. So question, how did you train your ANNs? Do bioconstraints plus nonlinearities influence training speed and convergence? If yes, how did you control for that? So it's sort of three questions. I guess the first is, how did you train your ANNs?
Yeah, this is a great question. So these ANNs were trained using the backpropagation of error algorithm in PyTorch, where everything was just all trained exactly the same. The formulation of the models were just slightly different with each of the different biological constraints. And when it came to the constraints and nonlinearities, I'm not exactly sure. I don't think I kept track of the training speed and convergence, but in the Glero 2011 paper that I mentioned, that talks about ReLU, the benefits of sparsity imparted by ReLU, compares the ReLU nonlinearity to a sigmoidal nonlinearity in deep networks. And they found that ReLU nonlinearities led to faster convergence in training speed. So I think that revisiting this work, it would be very interesting to see how these different nonlinearities would influence these. So I think this is a very good question. I didn't necessarily control for training speed, but I did use early stopping for points of convergence for all of these models. So I didn't stop them all at the same time. I used early stopping when they stopped changing in their objective function.
Cool. So yeah, Michelle says thank you. I think that was very clear answer. So thanks. Mm-hmm. Yeah, I guess I had a few questions, but so the first one was about the synaptic repetition. So essentially, maybe I was a bit confused, but so if you have a single pixel in MNIST in your sort of 4 repetition model, it's saying that that pixel has 4 synapses into the neuron, into the network, right? Or is that wrong?
So I'm just going to navigate myself over to that particular slide. So your question was, if you have 4 different pixel inputs received by the network, and then what was your question exactly?
Sorry, yeah. So I guess it was, if you have a single MNIST pixel, it maps onto a single one of these like trees. So like the dark blue here, or it's mapped into multiple different. How does it map into the network, the structure?
Yeah. So if you look at this cartoon of the dendrite, you can see that these are 4 unique inputs. So that would correspond to 4 unique pixel inputs. Okay. And so this, of course, is very simple. MNIST is images are 784 pixels long. So this is actually, it would need to be wider and deeper. And when I do the synaptic repeats, I take the same exact 4 unique inputs, add another subtree, and repeat those inputs exactly again. So there's no change between each subunit. It's it's a very extreme version of synaptic repetition. For example, this could be another limitation of the work, but it could open up another line of inquiry, which is if you include synaptic repetitions in a neuron model, to what extent do you want those synapses to vary, and the number of those repeated synapses to vary, and where do they go?
Okay, no, I think I understand a bit better now. So for MNIST, this does, I can't remember, the 700 and something. So there's like 700 and something, and then every time you repeat that k times, you repeat that whole vector, right?
Yes.
Okay, cool. And then, so then I guess, and then you have learnable parameters for each synapse, right? You said you had 5 learnable parameters per synapse?
Yes, only in the synaptic nonlinearity condition. So not here, but yeah.
So then I guess something that's maybe interesting is then if you look at the same pixel across different, I'm getting a bit confused with the terminology. If you look at the same pixel across different K trees, do they learn a similar distribution of those parameters, or is that heterogeneous across the trees?
Yeah, so that's a really good question, which kind of gets it back at, you know, if each subtree is receiving the same exact input and they have the same exact structure, are the synapses in their degrees of freedom allowing them to use or transform the information differently? And when they do learn, do they just like segregate, I guess, if you were to compare repeated synapses next to each other? I think that's a very interesting question. And I think that I haven't necessarily done that that analysis, but I did I think it's in the supplementary figures. I wish I would have included in this talk, a slide in this talk, but there's some histograms of synaptic inputs all lumped together, and you know, and synaptic outputs and what they all lumped together, and seeing how they are distributed after learning, which is like a more of a wider output, a wider, how do I say this? After you have an initialized synaptic, you have initialized synapses, and the output of those synapses have a very narrow band on this histogram. But if you train it, this band widens to use the full range of -70 to 50. It's not uniform. It's still like kind of peaky at 0, but it's, I think it does. They do change, but I don't think they change you identically, right? Yeah.
Yeah. No, that's interesting. I think I think that could be interesting to do some more analysis of that. Because you could imagine doing things like, I don't know, some sort of like clustering or similarity to say like, are some of the branches more similar? Do the branches form like groups of types of branches and things like that?
Because like each branch or subtree seems to kind of be similar to like an ensemble or like different assemblies of you know, of doing different computations on each tree, perhaps, and you know, it's kind of like maybe a winner takes all kind of thing.
I guess you could imagine finding a method as well to decide on the number of subtrees to have. So for example, if there's, I don't know, 10 types of subtrees roughly, then you can sort of prune to 10 subtrees, because you say the rest of the subtrees are basically repetitions of these subtrees and stuff.
Right, there could be redundancy. This would be a very interesting line of inquiry. Yeah, a very good question.
Yeah, there's another question in the chat. Actually, people in the chat, you're very welcome to come on video and ask your questions if you like. Kareem, I don't know if you want to, or I can read your question for you. I'll read Kareem's question for him. So Kareem Hashabi says, great talk, thanks. Why do you think repeating trees helps? A general question, do you think the computational neurons need to have all these properties, or are there various kinds of neurons?
Yeah, so to answer the first question, one of the ways, one of these ways is that the repeating of the trees. Let me see if I can get the slide up here just for a visual aid. Oops. So I'll just answer the question. So, right. So when you have the synaptic repeats, in my hands, I repeated each subtree, and what that does is that each of these black lines here corresponds to a weight. That in an OG artificial neural network, it's really just a series of weights dealing with activations and, put through nonlinearity. So the weights are learnable and provide a degree of freedom, an additional degree of freedom for the network to then learn and then converge on a solution closest to your target sooner or more effectively in ways that generalize more. So what I'm doing by adding each of these subtrees is I'm adding more degrees of freedom to the model, allowing it to then possibly learn the task much easier. And so, I'll just say that I'll make a bit of an aside on this, which is like biological neurons are very complicated and seem to have, all of these various details or weights, or if you want to consider it continuous, it's very, it has a lot of degrees of freedom. So you could say that, well, I guess the next question I would put forward is what weights or what parameters of a neuron model that are sufficiently detailed corresponds to a degree of freedom that a biological neuron actually uses when it is plastic and learns to compute. So that's my first, sorry, I kind of talked for a while about that one. And do I need all of the computational neurons to have all of these properties? I don't know. So these are constraints that we just kind of realize, wait, we can formulate this and put it into a model. What does it do? I think that this is the beginning of a good deal of work that really does pinpoint down to what extent is this particular property going to contribute to computation? Is it relevant to questions of computation, or is it not? And I believe that using this type of method where you are taking an optimizable neuron, basically, and setting it to the task of performing a task, you are basically measuring or using that task as a bit of a metric for how much this particular biological property is contributing to the neuron's ability to learn and compute. And if it doesn't, then maybe it's not relevant to computation. But if it does in a significant way, maybe it does. I think that another way this line of questioning could be expanded is to think about different kinds of neurons. You mentioned, are these constraints necessary for every neuron in the brain? That's a good question. I don't know. I think that when it comes to specifying your neuron model, choosing properties or finding parsimonious properties where one neuron has one type of property, another neuron has a different kind of property, not the previous one, then maybe you can start making some theories about, like, are thalamic neurons computationally more powerful than CA1 hippocampal neurons, or vice versa, I think this is a beginning of a lot of, these are really good questions and kind of point to future directions.
Yeah, no, thanks for that answer. I think also it sort of goes in the direction I wanted to ask a little bit about, which is, I guess, have you started to think about making like, yeah, networks of neurons like this? And then once you had networks of neurons like this, you could start to explore this heterogeneity a bit more as well, right?
Yeah, I think that that's also a really good future direction for this kind of work where, you know, you have basically a network of optimizable neurons. And you want to you could optimize the neuron specifically, you could optimize the whole network itself, and allowing for the neurons to have heterogeneous properties that are converged on through the process of learning. And I think that that could be definitely a direction that we can go in terms of exploring this space, and perhaps even thinking about like what are the properties that are converged on when you have a network of neurons that are optimized toward a task. And yeah, I think this general framework of thinking about neuron models as optimization questions allows us to be able to ask this put this normative spin on it, where we say, okay, a neuron should be able to perform this kind of task. When we use this method from deep learning, what do we find? And what properties come up? Like, for example, your question about like the perhaps separation of synaptic activities after learning, and how that might be impacted by synaptic repetitions. It's very interesting.
Cool. No, I think that seems a really exciting direction.